Hello. Good evening to all of you. Welcome to the third live session of the NPTEL course Design of Reinforced Concrete Structures. I am Sanjay Kumawat. Today we will be discussing a total of three questions. All of them would be on calculations of ultimate resisting moment of three different types of sessions. Let's begin with this session. Okay. Uh, before going to the three questions, we will be first clearing up our or refreshing some of the concepts which would be very useful for solving these three problems. So you all have already studied the different types of sessions in the week 2 or week 3 content of this course. So I am just revising them. So here you have a singly reinforced beam, as you can see it here. This is a singly reinforced beam. This is a singly reinforced beam, a rectangular beam of dimensions B by D, and it is being reinforced with three bars in the tension side. Uh, Sumalanta, can you please mute yourself? Okay, thank you for that. So what I was explaining is we have a rectangular beam here of dimension B by D, and it is singly reinforced. That is, it is reinforced only in the tension side. Now, what important we need to study is we have two types of equations or two types of diagrams for this singly reinforced cross section beam. So firstly is the strain diagram. This is the strain diagram, and the assumptions which we use to draw this same diagram, this strain diagram. Can any one of you tell me what type of assumption we used to draw this strain diagram? This is the strain diagram which shows strain in concrete and the strain in the reinforced concrete, in the reinforcement in this beam. Can any one of you tell me what assumption do we use to draw this strain diagram? No one? Okay, so I will only tell you. The assumption which we used for drawing this strain diagram, this is very important. This is many times asked in gate examinations also. That is the all tensile forces taken by the steel. Okay, that is one of the assumption, but I'm asking you what assumption is used to draw this strain diagram. So let me tell you, the assumption which we used to draw this strain diagram is plane section remains plane before bending and after bending. So after bending also, this line, if you see, this line shows us the cross section before bending, and after bending also it remains straight. So plane section remains plane before bending and after bending. That's from this assumption we get this strain diagram. If we have some assumption, suppose plane section does not remain plane, then this diagram would not be a linear diagram. It would be some non-linear diagram. It can be anything like a parabol or something like that. But for our simplification, for mathematical modeling of different types of cross section, we are assuming it that the strain remains plane before and after bending. So now what are all these values? 0.0035. So 0.0035 is nothing but it is limiting strain in concrete. That is, this is a crushing strain in concrete. Beyond this strain, we does not allow it to go in the concrete. We are assuming that the concrete will fail if it goes beyond this strain. Okay. Now on the other side we have tensile. This is, you can see the nature of this graph is opposite. This is, that is the, this is, if we denote this by positive sign, for example, let me switch on my pen. Okay. If we denote this by positive sign, then this is negative. That is, if we denote positive on this side, then this is compressive and this is tensile. Tensile is entirely taken by the steel. Okay. So this is the assumption which is used for drawing the, what it is used for drawing the strain diagram. Now, this I have already told you that for concrete we are taking what? We are taking the ultimate tensile strain as 0.0035. But what about the strain? What strain we are assuming? Can any one of you tell me what strain we are assuming for steel? For steel, we are assuming yield strain. That is this value 0.87 Fy by Es plus 0.002. Let me write it here only. Okay, so this is the strain value we are assuming. This for, so last time only I have explained you from where this 0.002 comes. If you remember, this 0.002 comes, it comes from the inelastic strain of the reinforced bar. Okay, 0.002. Then this is from the linear part of that graph, if you all remember from the previous lecture. So this is the strain in steel. Now let's come on to the other diagram. This is the strain profile, this is the stress profile. So stress profile, what does it shows? Stress profile, which assumption do we use for drawing the stress profile? Now I think Piyush, what answer he gave before, that answer is valid for stress profile. What we assume, we assume that all of the tensile forces are taken up by the steel. That's why we can see that nowhere in nowhere in the beam which is having steel, here in this part we have no steel, so there is no part which is taking the tensile force. The only tensile force which is taken up is by the steel. And in the compression we can see that we have assumed a parabolic variation of compression force. Now from where does this parabolic force come? Let me explain you this also. So it would be like, you don't have to mug up much things. So you know the stress strain profile of concrete, we have the stress strain curve of concrete something like this. Okay, so we know if fck is this, if we have fck, that is the characteristic strength of concrete, then in order to consider various uncertainties in concrete, such as the fck value which we get for concrete is, it is we get it from a cube by testing a cube, but actual structure it won't be cube. So to take into consideration the slenderness in the concrete and the various other factors, because concrete is an inhomogeneous material, what we do, we consider 0.67 times of fck. Okay, now we will be applying the partial factor of safety to this. We have studied all of this in the previous class of mine, so you, if you have seen it, then it would be more familiar for you. So now we will be applying partial factor of safety to this, to this 0.67 fck. So what is partial factor of safety for concrete? Come on, put it in the chat box. 1.15. Okay, is it 1.15? Then what is it, what is the partial factor of safety for steel?
So 1.5 for concrete.
Yeah, it is 1.5 for concrete. So what we will be doing for finding the design strength of concrete, we will divide this 0.67 fck by 1.15. So this value will be approximately coming out to be this only, nothing else. So now you can see the nature. Let me draw it properly over here. You can see our graph is, first it is linear, then it is coming to be, it is becoming a parabolic path. So from this variation, from this stress strain curve only, we have drawn this, we have drawn this variation of stress profile here. Okay, so it is coming from this stress strain graph of concrete only, nothing from else. So here you can, now you can see, now the linear portion we are assuming it to be varying up to 0.002 strain, and the maximum value of this strain we are allowing it in the concrete is 0.0035. So this is the stress profile, this is the sorry, this is the strain profile, this is the stress profile. Please remember these two diagrams. This similar type of diagrams you will be using it for all other sections, whether it is singly reinforced, doubly reinforced, whether it is flanged beams, T beam, L beam, anything, whatever it may be, because whatever material we are using in these different types of beams is nothing but concrete and steel. So for concrete we have the variation of compression force in this way, which is coming from this stress strain diagram, and we are assuming that uh, this stress diagram, it is actually plotted for cracked section. So for cracked, in cracked section the concrete does not take any tension, only the tension which would be taken is by the steel. So steel what stress it will be taking, fy by 1.15, it will give us 0.87 fy. Okay, so this was all about the strain profile and stress profile. So let's proceed to the next part now. So what I have used, so from these two profiles what will we have, we can generate two equations from these two profiles. For from the strain profile we can have strain compatibility equation. So this is the strain compatibility equation, this is the neutral axis. Up to neutral axis we are assuming the actual depth of neutral actual depth for actually for balance section we have the actual depth and the limiting depth equal, but the neutral axis it always lies at the limiting depth of neutral axis. Then from this strain diagram by the similar triangles we can get this equation from strain compatibility. And what type of equation can we get from stress profile? Can anyone of you tell me? See, this is very simple. You should know the stress and the strain profile, then you can generate two equations and then you can design your session very easily. Okay, so what we can do with this? Yeah, we can play with this also. What we can do, we can apply stress equilibrium. We can equate Cu equal to Tu. For equilibrium, these two should be equal. Okay, fine. So from strain compatibility, I got this equation, and from this equation, now after solving this, I can get this simplified equation xu max equal to k into d, where d is the effective depth of this beam and k is nothing but k depends upon the various grades of steel, because the only variable in this equation is Fy. Okay, Fy depending upon different grades of steel it will be changing, whereas modulus of elasticity of steel it almost remains it almost not, it always remains constant. Okay, so K will be varying 0.46, 0.48, 0.53 depending upon different grades of steel. I think this is very clearer to you now. Now let's go to the further slide. Okay, now let me discuss this also. This is also very important. Now we have seen the different strain profiles. Now this is the limiting depth of neutral axis. Now based upon the strain in concrete and steel, we can classify different types of section. Okay, so here if the strain in concrete and the strain in steel, if they simultaneously reaches to its yield value, and in case of steel, and to the crushing strain in case of concrete, if they both reaches simultaneously, then we called it as balance section. Okay, now coming to the under reinforced section. In under reinforced section what will happen, our strain in concrete it will exceeds the yield strain. What does that mean? The yield, the strain which is present in the steel, it is more than its yield strain. And whatever strain we have in concrete, that strain in concrete has not yet reached to its crushing strain value. Okay, or else what we can say, for equal value of crushing strain in value, that is if the concrete has reached to its crushing strain value, then the strain which is present in the steel it is more than the yielding value. So this is the under reinforced. So under reinforced, what does it mean? That is the failure in the steel it will occur prior to the failure in concrete. Now let's look at the other case. The other case is over reinforced section. So in an over reinforced section what happens, when the strain in the concrete is equal to the crushing strain, then the strain in the steel it is less than the yielding strain. That is the yielding strain in steel has not yet reached. That is steel it has yet to take more moments, or it can take more loads. That, but our concrete cannot take more load in this case. That, what does that mean? The concrete will fail prior to the steel. So these were all the three cases. So just remember, the limiting depth, the actual depth of neutral axis will be greater than the limiting depth of neutral axis. This you can, I think there is no need to remember, just remember the concept. What concept you have to remember? Just assume that the strain in the concrete has reached. Okay, now the strain has in the concrete has reached to 0.0035, but for that strain, if the strain in the steel, if it is greater than the yield value, that means it is now going towards failure. So that is under reinforced. That is the reinforcement has reached to failure point before the concrete. Now for the crushing strain in concrete, when we look at the strain in steel, it is less than the yielding value. What does that mean? The steel it can take even more load, but the concrete cannot take more load. That is, now our section is over reinforced. So we never go for over reinforced section, because in over reinforced section what happens, concrete fails prior to steel, and the failure of concrete if is a brittle failure, so it does not give any warning and there is a sudden failure. Whereas we go for under reinforced section, because in under reinforced section, since steel is a ductile material, the ductile material what happens, it gives prior warnings. That is, we can see cracks, and because of that warning we can, what we can do, we can evacuate the building or so. So it can give us prior warning. Or the worst what we can do, we can go for balance section. That is, the strain in concrete as well as in steel they reaches simultaneously. Here I have shown you the crushing strain of concrete and the yield strain of steel. So I think this is very clear to you. So now let's move on to the first problem of today's class. So let me read out this problem. The problem says a singly reinforced beam 300 mm by 550 mm is reinforced with 4 bars of 20 mm diameter with an effective cover of 50 mm as shown in the figure. Okay, so this is the figure. Determine the ultimate moment of resistance of the given section for this case 1 and case 2. So we will be looking at the case 1 first, then we will be jumping to the case 2. So here you can see the cross section of the singly reinforced beam. It has a width of 300 mm and effective depth of 500 mm with a 50 mm cover, and there are 4 bars of 20 diameter. For the case 1, these bars will be assumed to be of Fe415, and the concrete grade would be assuming to be of 25 MPa. Okay, so these are all the given data. This is all I have already read out. The only thing I need to mention is I have calculated the area of steel for you. What we have to do, we have to determine the ultimate moment of resistance. So how we will be doing it? So ultimate moment of resistance, we can calculate it easily from the stress profile. Okay, stress profile, if you see it here, what we will be doing, we will be calculating the cu value, we can multiply it by the lever arm, and cu into lever arm will give us the ultimate moment of resistance. So for cu, for calculations of cu, what we have to do, we need to first calculate the actual depth of neutral axis. We have to see whether the section is under reinforced, it is balanced, or it is over reinforced. According to that, we have to find xu. Now there would be many things are involved in calculating of xu. As we are proceeding with the problem, I will make things more clear to you. For the timing, please keep patient. So the problem statement is to calculate ultimate moment of resistance. So how we will be proceeding it? First, the case one is Fe415 and M25. So first we need to calculate the maximum depth of neutral axis. Okay. So how we can calculate that maximum depth of neutral axis? Can any one of you tell me? Come on. I have already told you we have two equations from two profiles. First is the strain profile, the second one is the stress profile. From strain profile, I have already shown you XU equal to KD. So that is the maximum depth of neutral axis for balance section. Okay, so here I have given you this equation, or else you can directly use that K into D. For 415, it is I think 0.48 times D. You can substitute Fy value, you can substitute ES value, and you can calculate the XU max. So what XU max I am getting it for this problem is 239.6. Okay, now this is XU max. This value of depth of neutral axis, it is for balance section. You get me? Why I am saying this is for balance section? Because what we are doing, we are using strain compatibility equation. In strain compatibility equation, we are assuming the strain in concrete as 0.0035, we are assuming the strain in the steel has the yield strain 0.87 fy by es plus 0.002. Okay, by assuming this, I am calculating the xu. So for this calculation, I will get the maximum depth of neutral axis, which is for balance section. Okay, now I don't know whether my section is balanced, it is over reinforced or under reinforced. I only know for balance my XU should come out to be this value. So how to know whether our section, whether it, what type of section it is, whether it is under reinforced or over reinforced? Can any one of you tell me how to know this? Come on, no one.
We have to calculate XU value.
So how to calculate it?
Using C equals to T means tension equals to compression in where that neutral axis is present at that place. So the formula is 0.87 F by AST upon 0.36 FCKB.
Okay, so uh, it was a very good answer. So let me simplify it. I have told you have to remember only two diagrams, strain profile and the stress profile. So we have already used the strain profile for calculating the maximum depth. Now the other one what is remaining is the stress profile. So from stress profile, what we can do, we can equate compression force equal to tension force. Okay, so compression force is nothing but 0.36 FCKB into XU, that we are equating it with 0.87 FY AST, which is the tensile force. So after equating these two, what I get is actual depth of neutral axis. Now this depth is for our section because I am using the section properties in this ast and the fck value and the b value. These are all my section properties. So for this section properties I am getting the actual depth of neutral axis. Now you can see this xu, it is less than xu max. Okay, what does this mean? What does this mean? For balance,
Under
uh, yes.
under reinforced section.
Under inputs.
Okay, so this is under info section. So let me elaborate this to make you more clear. So what is happening here? Now for balance section, I know this. For balance section, I have this diagram. So this is XU max. And now I am getting the XU value less than this XU max. What does this mean? This mean my diagram will be something like this. So you can see if I assume the strain in the concrete to be 0.0035, my strain in the steel will be more than, it will be greater than this value. Okay, so this is an under reinforced section, so it is fine. I can design my section to be under reinforced. And one more thing, this is very important. See, pay attention. In the last class I have shown you the stress strain profile of steel. So it was something like this. This is the stress strain profile of steel. What I have told you, for this value, sorry for the bad diagram, but please manage. This is fy. So for this value our yield strain occurs. This is 0.002. Now what I am saying, my strain in the steel, it is greater than this value. It is greater than this value means it can be anywhere into this graph. So is it fine if I still assume f, the stress in steel, this value? Is it fine? Can I assume this
Yes,
value? Yes, it is fine because now we are going into the constant zone of this graph. So please remember this, for under reinforced section, the strain in the concrete is greater than the yield strain, but still we will be assuming the stress to be 0.87 Fy because we are in the constant zone of this graph. This is very important concept. Please remember this. So everything is fine now. For under reinforced section, there is no problem. I know XU is less than, so this is under reinforced section. And let me delete this first. Okay, so I can calculate the ultimate moment of resistance as 0.36 fck b into d minus, this is d minus 0.42 xu. You all must know this. I am not showing you the derivation now. So you can substitute the value and find the ultimate moment of resistance very easily. Okay, so this was the first case. Let's move on to the other case. Now what we have FV 500 and M25. Okay, so let's see, again we have to calculate the ultimate depth of sorry, again we have to calculate the ultimate moment of resistance. So for that also, now the grade of the concrete as well as the grade of the steel has changed. So we need to again calculate the maximum depth of neutral axis by using the strain profile. From strain profile I get this equation, or you can use directly 0.46b. So this is the maximum depth of neutral axis. This occurs for balance section. Now the second is calculation of depth of neutral axis, the actual depth which is coming from the properties of our cross section. Okay, so that we can calculate it from stress profile, that is equating C equal to T. So I'm getting now 253.10. So XU, actual depth of neutral axis, it is greater than XU max. So what we can conclude now? Come on. What type of section is this?
Over input.
Over reinforced. Okay, so you all know this. This is over reinforced. But to make now again, to make your concepts more clear, let me again draw this. This is for your benefit only. So suppose this is for balanced. Now let me draw this for over reinforced. So our actual depth. Now we are saying that the strain in the concrete, it cannot go beyond 0.0035. It cannot go beyond this value. But XU is greater. That means it is greater than this value, that means it will come over here like this it will. Okay, so what does this mean? What does this mean? The strain in steel, it is less than this value, 0.87 fy by E plus 0.002. Okay, the strain in our steel is less than the yielding strain. Now again I would like to remind you about that graph. That graph I think I have shown you now here. So you all now agreeing that there is the over reinforced section, but for this over reinforced section we know that the strain is less than the yielding strain. But what problem we will be facing with this thing is, let me erase this. Okay, so this is the over reinforced section, but from the previous class we know that, what we know that our strain now it is less than the 0.87 fy. That means the strain it must be lying in this non-linear zone. We don't know whether it is lying in this non-linear zone or whether it is in this linear profile, but now this is very definitely confirmed that I cannot use 0.87 fy now for over reinforced session. So I am using fy here has 0.87 fy, so that is wrong. This is also wrong. So I cannot proceed with my problem further before I know that what is the actual stress in my steel. So it is very important that you know the previous problem which I solved in the previous session. You should be very thorough with that problem. Then only you would be able to understand this. You are getting me, Hannah? Are you all getting me? Type yes in the chat box if you are getting.
Yes, sir.
Okay, fine. So for over reinforced, we need to calculate the actual stress value. For calculating the actual stress value, we need to find the we. So what will assist you is you will be assisted by the various inelastic strain and the design strains. So this will be given you in the question only. This will be provided. So if your session is over reinforced, you will be needing to calculate the design stress values. So how we will be calculating it? I already told you we have only two equations, one from the strain profile and one from the stress profile. Using these two, what we will be finding? We will be finding the actual stress in the steel. So how we will be doing it? Let's see it. Let me show you first. So I will have to assume some xu value first. So this is not the actual xu because I am using yield stress here. So this is not the actual value of xu. So now what I will do, I will assume some xu value. I will substitute that xu value in this equation. Then I will calculate. Okay, sir, in our class it is said that for getting moment of resistance, we have to compare mu due to concrete and mu due to steel. Okay, so you can compare it. That is not an issue. Actually, in the previous problem, I have given you the mu due to concrete only because if you calculate the moment of ultimate moment of resistance due to steel as well as due to concrete, both values come out to be same only. Okay, you are saying that the less of the two should be used. I know what you are saying, but now we are using the crushing strain of concrete only, so that's why I am using the concrete value only. That is fine, no issue with that. Okay, so where I was saying you should assume one xu value, substitute that xu value here. After substituting that xu value, what you will get? Okay, let me write it here. What I am saying you that you have this, what this is epsilon st. I don't know what epsilon, what value is this. Now what I am assuming, this is 0.0035 always. This is the xu which I will be assuming. So what will be this value? This will be d minus xu. So from similar triangles you can do oh sorry, this is not d minus xu, this is d minus xu. So from similar triangles you can easily find this 0.0035 divided by xu. equal to epsilon st divided by d minus xu. So I will assume one xu value randomly. Assume this value, suppose this is 253.1. So for this xu value I will get epsilon st, that is strain in the steel. Then using that strain in the steel, I have to compare that strain in the steel with this given values. Suppose it comes in between these two strains, and for that strain we need to calculate the stress values which would be coming between these two stress. So for that strain I will get the design strain of steel, and that design strain I need to substitute it in the stress profile equation, that is c equal to t. In this equation we have to substitute 0.87 f, sorry, now we will be not using 0.87 fy, we will be using what fst I get it from this equation. Fst into ast divided by 0.36 fck into b. Now we will get this xu. So this xu calculated, it should come equal to this 253. If it does not comes equal to this 253, what I will say, my assumption is wrong. Okay, then I will assume some other value. I will assume a value less than this. So we have to carry out this type of iterations. I hope I was able to explain you this. If anyone has doubt, they can unmute and ask me. I hope you are able to understand what problem is with over reinforced section. We the stress in the steel we don't know. So here I have already calculated the different values of design strain and design stress for different assumed value of XU. So firstly I have assumed 253.1. For that I got the design strain. From where did I got the design strain? From the previous table by using the interpolation. You can use the interpolation. I don't know if you are not familiar with linear interpolation. I think you should go and learn it. It is very easy. So by linear interpolation I get this design strain. For this design strain I can get this design stress. Okay, and by this design stress I can again substitute it into the c equal to t equation, and I get the xu calculated. So these two are not equal, then I again took some other value, still they are not equal, then I took again some value, now they are coming out to be equal. So I can use this xu value for as the actual depth of neutral axis, and the actual design stress in our steel is coming out to be 428.3. Okay, so for when I substitute 428.3 for this value, for this XU value, when I substitute it here, I get the ultimate depth of, ultimate resisting moment. So, sir, please provide recording video of this class. Yeah, recording. Yeah, it will be provided to you. Don't worry. Fine. Fine. Anyone has any doubt? We have studied two problems up to now. First was the under reinforced, the other one was the over reinforced. For over reinforced, we had some problem with the stress in steel. We don't know what was the stress in steel. So we have calculated that stress iteratively by assuming different values of XU. How we can do it? We have only two equations, one from strain, one from stress. By using these two equations, I can iteratively calculate XU and find the design stress. Okay, fine. Now I am proceeding further.
Sir, if we just use mu limit value, the formula for that, then what is the value? Is this value lesser than that or greater than that
What
if
do
you
you,
use mu limit?
what do you think?
I think so. This uh, it will be lesser. I don't know, sir.
You don't know. Okay. So I think you should explore it by yourself. It is a very good question. So Shivam, why don't you do it by yourself and tell me in the next class? I know the answer. Don't worry. So I can explain you. See. So this is the answer. The maximum depth of neutral axis we got 228. So this is for balance section. Okay, so the limiting depth, the limiting moment of resistance, you will calculate by using this XU only, now. But that XU value you are calculating it by assuming some Fy value. That Fy value you are assuming that it is the yield stress. But this is 228. Now, when you look at the actual depth of neutral axis, we are getting it as 249. It is greater. Do you get me? So this is a greater value. After substituting this greater value, I am getting this UR.
So it is greater.
Yeah, because for over reinforced, what is happening?
For over reinforced, the XU is increasing, means moving downward greater than XM.
Okay, so what will happen?
Then means then moment of resistance will increase.
Okay.
Means
No, it's not like that. See, let me explain you. Limiting moment of resistance will always be greater. See, you cannot notice this minus sign. We are subtracting it from D.
yeah.
So this will be the greater the value of XU, the less will be this the bracket term. So the less will be the bracket term, less will be our moment of resistance. So if you are calculating it by using the limiting depth of neutron axis, what you will be doing, you are not designing a conservative section. You are overestimating the capacity of our section. So that is not good.
Yes, sir.
So that is not good. Okay. So yeah, you are right. Always the limiting moment of resistance, it is always greater. That's why we call it limiting. So let's look at the other problem now. So now, up to now we were looking at rectangular sections. Now I will be showing you one problem on T section. Okay. So this is our problem. Here also we have to determine the ultimate moment of resistance for this isolated T beam. So this isolated T beam, why I am using this term isolated specifically, because in code you have two formulas for calculating the width of flange. First one is for continuous T beam, the other one is for isolated T beam. Okay, so this is an isolated T beam and you have these various given parameters. The width of this beam is 1000 mm, the depth is 100, and all of this you can see. I will only read out the important one. FCK is 20. Steel we are using is of 250 MPa, and there are six number of bars in the tension zone. So the area of the steel I have calculated it for you. Now what we have to do, we have to calculate the ultimate moment of resistance. So you all must be familiar, for T beam we are having three number of cases. What all are these cases, I will be explaining you, just keep patience. So the case one, okay, so this is the case one. So in case one, what happens, our XU, the actual depth of neutral axis, it is less than, just a minute. So our actual depth of neutral axis, it is less than the depth of this flange. So when it is less than the depth of the flange, our entire compression it is taken up by the flange only, and all of this tension it is taken up by the steel. So now this T beam, for the first case, it would behave like a normal rectangular beam only. So this part it will be behaving like what? This part will behave as the compression concrete, and this will behave as the tensile steel. So this will be our normal rectangular beam only. You can directly use this formula 0.36 FCK into XU, and you can directly calculate the XU value. Okay, by equating C equal to D, I had directly calculated the XU value. But after calculating the XU value by using the case one, what I found that this value is coming out to be greater than the depth of flange. So what is the depth of flange? Depth of flange is 100 mm. Depth of flange is 100 mm, and the actual depth we are getting it as 131. So now this compression, it is not only taken up by the flange, but it is also taken up by this web. So this is the first case we cannot adopt. So the first assumption is wrong. So now let's move on to the case 2. In case 2, what we assume? In case 2, we assume that, okay, our stress it is greater than the depth of the flange. Our compressive stress it is greater than the depth of the flange, but we are assuming that the 3 times XU by 7 value it is greater than DF. So what is the significance of this? If you have carefully seen the derivation of this stress block, then you must be familiar with this. So this is not very difficult and I won't be explaining you here. But just to make familiar with this, what is happening here, if 3 by 7 xu, if it is greater than the depth of flange, then the rectangular part of the stress block, it will be lying outside the flange. That is the compression, some compression will be taken up by this T flange also, and some compression will be taken up by the web also, the linear compression one. And whatever the parabolic is, the entire parabolic part, it will be taken up by the web only. So this is the case 2. So case 1 and case 2 are very easy. What we can do, we can separate our T beam into two beams. The first will be only the flange, and the other will be only the beam. So the flange will be only taking up the linear compression part. So this is for the flange, the linear compression part. And our web, it will be taking the linear compression part as well as the parabolic compression part. So this will be now behaving as our normal rectangular beam. So the web will be behaving as a normal rectangular beam, whereas the flange, it will be taking up the linear zone. Okay, so now we have two C values. We can add up this CW plus CF, it will give us T. So I can calculate this. C will be the compression in the web and the compression in the flange. I will be equating it with the total tensile in the steel. After equating it, I will get XU value. So after calculating the XU value, again I found that this is again less than 7. So this is also our assumption. This is also wrong. So what is the third case now? These are all very easy. You all can just play with it and learn it by yourself. I don't think this is a very difficult thing. Now the third case is what? Now the third case is that, what is the third case? Third case is that the depth of the neutral axis, it is in between df. And what does that mean? It means that the linear part of our stress, it is entirely lying into the flange, and the parabolic part of the stress, a part of it is lying into this flange, and a part of it is lying into the web. So now what we will be doing, we will be again separating this T beam into two parts, that is the flange part and the web part. So the web part, it is always easy. The web will, it will always behave like a rectangular beam. But when we come up to the flange, what will happen? In the flange, now we have the linear zone. So in the flange, if you see, I will show you. In the flange, now our stress variation will be like this. Sorry, this is the, okay. Let me delete it. So in the flange, this is the linear part, and the small part is parabolic like this. So I don't know what will be the centroid of this, and how should I calculate this stress into the flange. So because of this small green part, now we need to calculate the YF. I can calculate CF, YF by some derivation. You can refer it from any book. So YF is coming out to be this value. Again, now I can equate the total compression to the total tension. Now when I calculate the actual depth of neutral axis, I am getting it as 173.5, and now that value is less than the 7 df by 3. So now this case is correct one. Okay, so now I have the XU value. Now what I will be doing, I will be finding the limiting depth of neutral axis. So limiting depth for 250, it is 0.53d. So it is greater than XU. So our section is under reinforced. So under reinforced, we have already seen there is no problem for under reinforced. So we can now directly go for calculating the ultimate moment of resistance, which is this value. When you substitute everything, you will get this. So T beam and L beam, they are not much difficult. Only today's session, the main goal was only to clear up your concepts about the stresses in steels for different types of section. So suppose if our stress in the steel, if this was not under reinforced, then if this is over reinforced, then again you would have to do that iterations and calculate the actual depth by assuming different values of XU and using the different uh, stress and the strain profiles. But for this T beam, only the stress profile will change. You will be having a compression force of something like this, where YF this and TU will be this. So everything is same only. Just the thing is, now something is taken, some part of the stress is taken by the flange, while some part is taken up by the web. So this all are the three problems which I had planned to discuss in today's sessions. So if you all have any doubt in these three problems, you are pleased to discuss it with me. Thank you. Any doubt?
Where does this YF value comes from?
Yeah, that's what I told you. YF value, it is like easy. First we have this linear part, like you have to do some mathematics. We have this linear part and then we have the parabolic part, something like this. So we need to find the average of this. So you can refer some book and look at the derivation for this. Now I am not explaining you to, but the main goal or the main motivations from where this YF has come, that it should be clear for you. We have converted this, see, we have converted this block into an equivalent rectangular block which is of depth YF. So even you can play with it, you can equate the area of these two and calculate the YF. This is same for both 0.45 fck. This is equal to 0.45 fck. You can equate the area of these two and find YF. It is easy. Any other doubt? Any other doubt?
No, sir.
Okay, so I hope this class was helpful for you all. And derivations of some of these equations I'm not showing you here because that is not my purpose to take these sections. I am here to explain you more conceptually what is happening inside. And this derivations, it is only playing up with the areas of different stress and stress strain blocks. You can refer it from anywhere. So, if there is no further doubt, I would like to conclude this section, and we can meet up with some more interesting problem in my other sessions. So please join them. So that's what all about this session. You all can leave now. Thank you.
Thank you, sir.